Hi everyone. Today we're going to talk about support vector machine, the real machine. This is part 3 of a series of 3 lectures on support vector machine. We've been talking about support vector machine algorithms, the family of algorithms as supervised classifier. It's not based on probability. It's a binary classifier, and we've been talking about it as a linear classifier. In this lecture, we are going to look at how we can apply support vector machine classifiers to nonlinear problems. So again, this is part 3 of this series of lectures on support vector machine. So we started with maximal margin classifier, and then we continue with support vector classifier. Today, we're going to look at how we can transform support vector classifier into a real support vector machine for nonlinear classes. So we'll be looking at linearly separable problems. This is an example of a perfectly separable problem domain. However, most data sets are not this clean. They're messier, so we talk about support vector classifier, which tolerates misclassification. So has works with messy boundaries where classes overlap, but still you could sort of fit a linear line that separates most of the data points, and that's what we call a support vector classifier. Okay, so you will still have these linear lines. This graph shows perfect separation, but with a support vector classifier, you could tolerate a few misclassifications. However, not every problem is linearly separable. For example, this one. And we would even have domains like this where it's impossible to find a boundary at all. This actually is just one dimension. This is a two-dimensional space, which is consistent with the last slide where you have dots that surround the crosses. When you have a circular decision boundary like this, it's impossible to draw a line. So when you have a problem like this, linear support vector classifier is basically useless. What we will need instead is what we call a support vector machine. The machine is basically a support vector. It's an upgraded support vector classifier. We upgrade it with a nonlinear kernel. We'll talk about what kernels are. Kernels are mathematical transformations that are very efficient computationally. They help us transform low dimension data into higher dimension space, and we'll look at how that's done. There are some really popular kernels. There are lots of different kernels. The most commonly used ones are polynomial and radial. The support vector classifier we've been looking at is basically a support vector machine with a linear kernel. So you will actually see linear as the kernel parameter in the SVM command in R. So you can consider linear as one of the 3 kernels that we have available. So linear, polynomial, and radial. What is a kernel? Well, kernel is really just a computation of vector similarity, and we can actually reformat. So we have been looking at the support vector classifier equations. We can actually reformulate the equation as a function of vector similarity. What do we mean by vector similarity? So if you look at the dots, the data points on the graph, each one of them is actually a vector. So you can represent it as a vector starting from the origin. If we look at these 2 particular points, D1 and D2, these 2 points are can be represented as vectors starting from the origin x1, y1, and x2, y2. If we have 2 points that are very close to each other, that means they're very similar vectors. If you have 2 points that are far away from each other, then you can say these two vectors are not similar to each other. And we can actually quantify the similarity of these vectors with a very simple mathematical formula. So this is a vector, this is a vector, and we can just look at how close they are to each other. So how similar is D1 to D2? We can actually measure their similarity using inner product. So what is inner product? Inner product is written as the sign here, the brackets with D1 and D2, the two data points inside. So you can look at this vector x1, y1, and x2, y2, and we have the inner product is represented with a dot. Okay, so when we have this dot product, basically what it does is it's basically the first vector multiplied by the transformed vector D2. And then what we do is we multiply x1 with x2, and then we multiply y1 with y2. We add them together. Okay, so you would do the multiplication, you will add them together, and you will get a scalar value. That's the result. And that represents the size of the inner product between D1 and D2. So here's an example. If we have a vector D1 that's 1, 2, and then a vector D2 is 3, 4, then we will transpose D2, and then we will multiply 1 with 3 and 2 with 4, add them together, and we'll get 11. So 11 is the inner product of these two vectors. Now, the inner product can also be represented this way as the length of D1. So length of D1 is represented as bar D1 bar. And then, so this is the length. This is D2's length over here. So the length over here, D2. Okay. So these two, you multiply, you measure the length of the two vectors, and then you find the angle between the two, and you get the cosine between the two. You multiply these three terms together. You will also get the inner product. So the inner product can be calculated in two different ways. Okay, so on the last slide, we saw one calculation. This is another way of calculating. You'll get the same result. Now, this is why inner product measures vector similarity. Okay, so when the angle gets bigger, cosine actually gets smaller. Okay, so and when the angle theta gets smaller, cosine actually gets, so cosine theta goes down when theta goes up. When theta goes down, when you have a small angle, cosine actually goes up. Okay, so because the cosine is the inverse of the theta, the size of the angle, when you have a very small angle, that means your cosine goes up, the inner product actually goes up. That means these two dimensions actually, because the angle is smaller, they're closer to each other, so they're more similar. So when you have two vectors that are similar to each other, you get a bigger inner product. So this is your inner product. Inner product will go up when the two vectors are more similar. When the angle is bigger, that means they're farther away from each other, they're less similar. I guess you have a bigger angle, which means the cosine goes down, the inner product goes down, so you get a smaller inner product. That's why we say inner product measures vector similarity. Okay. Now we have a very convenient way to measure vector similarity. SVM can be expressed simply as a function of vector similarity. Okay, so in this particular case, you can see that we have if we look at these 1, 2, 3 different dots, 3 different vectors, you can see that D1, D3, this pair, these two are closer to each other, so they're more similar than the D1, D2 pair. So this has a bigger theta, has a smaller theta, and so this one is more, D1 and D3 are more similar. So this pair is more similar than the D1, D2 pair. Okay, that means that this pair should have a bigger, this pair D1, D3 should have a bigger inner product than D1, D2. And what we do is when you have a data set like this, you basically can pick any pair of 2 points and you can calculate their inner product. In fact, what SVM does is it just goes through every single data point, and I'll find the inner product of that particular data point with all the other data points. So we find all possible pairs and we calculate their inner products and we add them up. And we do some transformation. That's basically how SVM works. It's really just a function of the total vector similarity. Okay, so if we look at this data set, usually this is how we represent a data set. We will have P features, so P columns across, and then we have sample size of n. So we can note the notation runs from 1. This is actually the second notation. This first number, okay, is i's 1 through I, so that iterates through the first row to the nth row. And then we have P columns, so we'll have the second number actually iterates through from 1 to 2 all the way to P. So basically we have an n times P space, right? N times P data frame. And every data frame, every data point, every cell is a data point, and every data point is basically a dot on the chart. So what we can do is we can calculate vector similarity between any pair of 2 data points. So let's say that we take these 2 data points. Vector similarity is inner product, just as a reminder. Right, so vector similarity can be measured by inner product D1, D2, basically any pair of 2 points. So if we take D11, D21, so these 2 data points, we can calculate its inner product using the bracket notation. We can calculate the inner product of these 2 points. We can take another 2 points. So these can be any 2 points. They don't have to be right next to each other. I'm just picking dots turned right next to each other so it's easier to represent. But in reality, you will actually go through any possible pair. So you could take this point and calculate their inner product. You can take this point and calculate the inner product. Okay, and actually you have to go through all possible points and add them up. So we will take 2 points and we'll calculate the inner product. And what we do is we fit the equation with an parameter called alpha. So instead of beta, remember beta is the coefficient for a variable, okay? Like x. Well, it should be beta 1, x1 actually. However, in this particular case, we're not using x's. We're not using the values for the x variables. Instead, we're using inner products in our calculations. So these are our terms as inner products as opposed to the raw data points. And so what we do is we would use alpha instead of beta as a symbol for the parameter that we're estimating for each of the inner product. Each of the inner products will get an alpha term, and then we basically just add them up. Okay, so you would take each of the alpha multiplied by the inner product term. So we'll have a term like this for each data point. And then we basically just iterate from I to n. We go through all data points. We multiply x with all the other data points. And so we get all the inner products. Every inner product gets an alpha, and then we add them up. And this part is actually our kernel. So the kernel is really just a summation of inner products. And then we have a beta 0, we add these up, and this becomes our SVM function. So how do we estimate this linear classifier? So this is our linear kernel, actually, because we are not squaring, we're not doing anything in dimension D. This is really just staying in the same domain. So this is a linear kernel. So how do we estimate this linear classifier? Well, this is the inner products of all possible pairs of data points. So we actually have n choose 2 number of pairs, possible pairs, and it's a lot of this number gets big very quickly. So if you have 1,000, a sample size of 1,000 times 999 divided by 2, so that's 500,000 basically pair of inner products. So each one of them, each inner product actually gets an alpha term. And then we get this equation, which we can solve using convex optimization, and turn out that the solution will reduce most of the alpha to 0. Okay, so this is actually an error, so this should be equal to 0 for all the other data points. You will only get a non-zero alpha term for the support vector. So we talked about what support vectors are. They are the points that are either on the margin, within the margin, or on the wrong side, the misclassifications. So only those will actually get a non-zero alpha. So most of the points, most of the alphas get squashed into 0. So you get lots and lots of 0 terms. And this is basically, like I said, this is basically what we mean by the linear kernel. This is just a measure. This kernel quantifies or adds up all the similarity of any 2 points. Okay, and then similarly, we can do a degree D polynomial kernel. So instead of this term over here, we're going to replace it with a kernel that is polynomial. So this degree D polynomial kernel is the original term. So this is the linear kernel. We add 1 to it, and then we just raise it to D's power, and that's how we get the polynomial kernel. So this is the kernel function, and this is the equation. Okay, so when you do a polynomial, when you fit a polynomial kernel, you will actually get the polynomial decision boundary. So this makes a lot more sense when you have this blue class over here and the pink class over here, and you want to be able to separate them. You do not want, if you just fit a linear kernel, it'll draw a line in the middle, which does not make any sense. Here with the polynomial, you actually get 2 decision boundaries. That is much more sensible. The radial kernel, again, we'll look at the inner product section, and then we'll replace that with a slightly different equation. So this equation, radial kernel, will actually work in infinite dimension. It will work in any dimension. So radial kernel is actually a very popular kernel right now because it can work, provide a solution to almost pretty much any type of decision boundaries. Okay, so the radial kernel looks a little scary, it looks a little different, and so we'll break it down and go through the components step by step. Okay, so you will notice that we are introducing a new term called gamma. It's a positive constant. We'll talk about what it is. Okay, so this is a radial kernel. When you fit a radial kernel, you will actually get the circular decision boundary. So this is your decision boundary. And it actually captures, so it's very, as you can see, it's circular, it's very nonlinear. The radial kernel is actually able to capture all sorts of shapes of decision boundaries. So we're not limited to linear classifiers anymore. So how does this work? Well, radial kernel, as you can see, this is no longer inner product. Remember, we used to have a term that's inner product, but here, this is not an inner product. This is a Euclidean distance. So this is taking 2 points, any point in any dimension, and we will just measure the Euclidean distance between the two, square that, and you will get this positive squared Euclidean distance term that's always positive, and we will just add them up. We'll do this for every variable, so you add them up across all p features, and that way you get a positive sum of Euclidean distances. So this whole term is positive. And then we multiply it with a tuning parameter called gamma. It's a positive constant, which we can tune using cross-validation to find the best fit. But basically, it's a number that we can, whose value can be changed by us for tuning purposes. And then, so this is a positive number. So positive times positive. Okay, so this whole thing is positive. And then we add a negative sign to it. Okay, so that means this whole term over here is negative. And then we do an exponent of a negative number, which will give us the kernel value. So the kernel value is basically the exponent to this negative degree. Okay. So if you think about this, the gamma is a positive constant, and then we can replace, so when we do testing, we will be given a new test value x, and then what we do is the kernel, what the kernel does is it takes the x value and calculate its distance from all the training data points. Okay, so this is again all possible pairs. And if your test value is far away from the training data set, then you will get large Euclidean distances, and therefore you will get a large term for this portion, the kernel portion, well, this portion of the kernel. That, because gamma is a constant, so if this term, the Euclidean distance total term is larger, then you will get a larger negative term over here. This portion is larger. And when you do an exponent of a larger negative, you actually get a tiny kernel. Whereas if you get a test value that is close to the training data set, then you will get smaller Euclidean distance total, which gives you a smaller negative term over here. This is a smaller negative term. And if you do an exponent of a small negative power, then you will get a larger kernel. So in this sense, this is how the kernel classifies the test values. Okay, so when the test value is closer to the training data set, you get a larger kernel. When the test value is far away from the training set, you get a small kernel. So in this sense, radial kernel operates very similarly to k-nearest neighbors sort of algorithm, and reminds us of local regression, which is using only numbers that are points that are close to you. The points that are far away are outside of the window, and they're actually not being used for calculations. So in a sense, radial kernel behaves very similarly to local regression or k-nearest neighbors, in the sense that only the points that are closer have more influence, meaning they give you a larger kernel. Points that are far away give you less influence, and that will give you a smaller kernel. Gamma. So this Greek letter is pronounced as gamma. Gamma is a tuning parameter, so you can turn it up or turn it down. So when gamma is larger, you get a more negative term. With the exponent, you will get a smaller kernel. When gamma is smaller, then you get a less negative term. With the exponent, you will get a bigger kernel. In the SVM command in R, you can specify gamma simply as a parameter, so that's very convenient. The gamma parameter is only available for the radial kernel. So these two have to go together. And that's it. So this is the summary of the SVM commands. You can see that for support vector machine with the radial kernel, the command is very straightforward. All you have to do is specify the kernel as radial, gamma equal 1. So this is, you have to specify the gamma if you're using a radial kernel. Now, if you use a polynomial kernel, you will simply say polynomial here. So polynomial in quotation marks. The nice thing about this SVM library is that it does multi-class classification, so Y can be multi-class over here. You don't actually have to do anything. You just have to have a Y. If your Y has, instead of zeros and ones, if it has 1, 2, 3, or even 1, 2, 3, 4, that means you have a multi-class target variable, and this function works just fine with multi-class target variables. Thank you very much.